Right, hello Year 7. I'm going to go through the idea of balanced and unbalanced forces with you today. You've been looking at types of forces and that you know that most forces will work in a pair. Okay, so the first thing I need you to do is, the PowerPoint for this is on class charts. Now these, you can click on them and try and match up the name of the force with its definition. Now if you can't get the PowerPoint to work, you can write these out on paper and then I'll give you the answers to those tomorrow. Okay, so that's your first little starter task. Now, when we talked about forces, you can't see forces, but you can see the effect of them. Okay, so you can't see a push, but you can see the movement of the object that you're pushing. And we actually show forces using arrows, and I started to get you to think about that yesterday. So we show the direction of the force using an arrow. So in that case, the man is pushing the car, so the arrow would be pushing towards the right. Okay, so in terms of representing forces, you can use arrow diagrams. Now, what you need to remember is that the arrow shows the direction that the force is working. Now, the second thing is that it also represents the size of the force. So these arrows are really, really useful. So in this case, we've got a football, we've got air resistance that's pushing up against the football, so this is a ball that's in the air, and we've got weight or gravity which is pulling that ball down. Now in this case, I can see the direction of both of those forces, and I can also see that weight, the gravity, is the bigger of the two forces, okay, because that arrow is longer. So in this case, the ball has been kicked, but now it is starting to fall again. Okay, so this ball would be falling because the weight arrow is bigger. Okay, and all forces are measured in newtons. Now we can show that in terms of the different sizes of the arrows, but we'll also talk tomorrow about the numbers that we can put onto this. Okay, so we can actually put numbers to it, but let's just concentrate on the arrows for the time being. Okay, so in this case you've got 2 force meters. Now you've probably used these in school to measure forces of different objects. Okay, so the spring and the little marker will move when you pull them. Now in this case, if you link the two of them together and pulled equally hard from either side, then you would record the same force from each force meter. So in this case, this one is pulling to the left with 10 newtons and this one is pulling to the right with 10 newtons. Now because those two values, those two forces are the same size, first of all my arrows are the same size, even though they're in opposite directions, they're the same size. Okay, and that makes my forces balanced. Okay, so because they're the same size or the same magnitude, okay, magnitude is a nice science word, although they're opposite in direction, because they're the same size, then the forces are balanced, so they cancel each other out. So the 10 newtons pulling to the left cancels out the 10 newtons pulling to the right. So in this case, the hooks don't move. Okay, oops daisy. Now, if we look at some examples of balanced forces, okay, so in this case, we've got a slightly different scenario. We've got the man here who's moving already. So we've got all these different forces acting on him. So we've got the two opposites here. We've got gravity and the reaction force of the bicycle that's holding him on the seat. We've got his legs that are providing thrust, okay, to push him forwards. And then we've got air resistance and friction by the wheels on the road that are acting to slow him down. Now, if these are all balanced, okay, then the man on the bicycle is going to carry on moving at the same speed. So if he was stopped and the forces were balanced, then he would stay stopped. But because he's moving, this arrow, the thrust arrow, if we added together the air resistance and the friction, these two added together would equal the same value as the thrust. Okay, so in this case, he is continuing at the same speed. So that's the other effect that balanced forces can have. Now in this case, we've got somebody who's skydiving. Again, we've got air resistance that's pushing them up with the air in the parachute, and we've got weight and gravity pulling them down towards the earth. And because these arrows are the same, the forces are balanced, so this person will fall at a steady speed. Okay, so they are going to continue moving at the same speed. Our skier, again, we've got our weight, we've got our air resistance and our friction. these forces are going to be balanced. So again, because the skier is moving, then they are going to continue moving at the same speed because the forces are balanced. Same one with the satellite. Now in this case, because the satellite is in space, there is no air resistance. Now if there's no engine on here, if it's not applying its engine, then there's no thrust. And because there is no atmosphere in space, there's no particles in space at all around it, there's no air, then there's no resistance from that air. So in this case, there are no forces. So our satellite, once you get it up there, this is the good thing about satellites, they just keep moving around and around and around. Okay, so they will just keep moving, they don't slow down, they don't speed up, they will keep moving at exactly the same speed all the time on their same orbit. Okay, so balanced forces can either, the object will remain still, okay, or it will continue to move at the same speed. Now, if they're unbalanced, so we've got the same idea here, we've got our 2 Newton meters joined together. If one side is pulled slightly more than the other, so in this case, I'm pulling to the left with 11 newtons and only to the right with 10, then these are going to be unbalanced, okay? So in this case, I will have what we call a resultant force. Now, because these 10 cancel out 10 of these, this force towards the left is still bigger, okay? So there will be movement towards the left. Now, if it is an object that's sat still, if there is an unbalanced force, then it will start to move. So in this case, if the force meters were sat on the desk and you pull towards the left with the slightly bigger force, then it would move towards the left, okay? If you are moving and the forces are unbalanced, then you will either speed up or slow down, okay? So unbalanced forces can affect you if you are still, in which case they'll make you move, or they can affect you if you're already moving, in which case you will either speed up or slow down. So we've got another little animation which shows some unbalanced forces. So in this case, I've got my man in the hot air balloon, okay, and this is where he's going to let his burner burn for a little bit. So at the moment, okay, the upthrust and the weight are balanced. At the moment, he's just pootling along, okay, because those 2 forces are balanced. If I increase the upthrust, this arrow has got bigger, then my hot air balloon has risen, okay, so it's continued to rise, okay, so it's actually moved. Right, the lady here, she's sat on a bit of a slope, right, in a nice car. Her handbrake is on, okay, I'm going to show you the forces. So we've got the weight here, got the reaction force of the road, and then we've got some friction. But because her handbrake is on, the forces are balanced to begin with, so she's not moving anywhere. Now if I take that handbrake off, I get unbalanced forces, and she will start to roll down the hill, okay. So the forces become unbalanced and she will move down the hill. What's the next one? Right, we've got our little dude on the motor scooter here. So again, we've got lots of different forces acting. We've got the thrust. This time it's from an engine rather than his legs if he was on a bike. Okay, so the engine is providing him with forward movement, air resistance because he's crashing into the air, and friction between the wheels and the road is slowing him down. Now really it's only these 2 that we want to concentrate on, because these are the 2 that will potentially change. The reaction and the weight will stay balanced. So if he increases, oh no, sorry, he's putting the brakes on. Okay, so he's put the brakes on. I'm just going to play that one again if I can. Just bear with me. Okay, so I'll show you the forces. He actually puts the brakes on, so that's going to increase the amount of friction, okay, and that will slow him down. So these 2 forces here become bigger than the thrust, and he will slow down. So unbalanced forces will either make something move or speed up or slow down. So you've got a bit of a summary here. So if the forces are balanced, the object will carry on doing what it was doing already. Okay, so if it was still, it will remain still. If it's moving, it will continue to move in the same speed and in the same direction. If they're unbalanced, okay, it will either move, so it'll either start to move, or it will change its speed. Okay, so it will either get faster or it will get slower. Right, let's see where we're up to. Now what I want you to do, these are the 2 little tasks, okay? You've got 4 diagrams here of 4 cars. And what I want you to do is I want you to copy out, you can just put a box if you don't want to draw the car, so just draw a square and write car in it. But for each of these diagrams I want you to tell me whether it is balanced or unbalanced. So you're just going to write next to it balanced or unbalanced. Okay, you don't need to tell me what the movement is, I just want you to tell me whether the forces are balanced or unbalanced. On this one, what you're going to do is you're going to draw them, and then you are going to add arrows. That's my doorbell. You're going to add arrows to show the size of the forces in each direction. So you need to draw the car, or you need to draw the object. You need to draw the arrows with the forces on with the right sizes to show what's happening. Okay.